Thank you. Good morning. Welcome to the first session talk after the keynote. My name is Fabian Hueske. I'm a Flink committer and co-founder of Data Artisans. As you've probably heard in the announcement yesterday, Data Artisans is the provider of the Data Artisans platform, which includes Apache Flink and the application manager. This talk will be about stream processing with Apache Flink, but using SQL instead of the DataStream API. The DataStream API is, or Flink's DataStream API, most of you probably know it. I guess most of you are here because you're using Flink in some kind of streaming context or you're interested in this. Maybe some of you also used the DataStream API in the training on Monday. And this API is a very expressive API. It gives you a lot of tools at hand to work with data streams. So you have windows, you have triggers, you have evictors. You can work with state and time, process function, methods to do asynchronous calls to external services, and all these things. So this API is really, really powerful, and you can do a lot of things with it. However, many applications don't really need this level of expressiveness. There have a lot of use cases have not so demanding requirements, and they can be specified more easily and more concisely with a domain-specific language. And what's the most popular DSL for data processing? You guessed it, it's SQL. So whoever has worked with SQL, worked with data has probably also used SQL or SQL at some point in time. Flink actually offers two relational APIs, which is the table API and SQL. Both APIs are basically two entry points to the same library, so they do relational data processing. And the most important thing about Table API and SQL is that both are unified APIs for batch and stream processing. So what does it mean, unified APIs for batch and streaming? This basically means that when you specify a query and you run this query on a file or on a static data set, the result will be the same as if you run it on a stream that contains the same data as the static file. So why is this important? This is important because for many use cases. So imagine you want to analyze historic data, like you persisted your stream somewhere in a file. You want to run a query over that. And now you want to compare these results with your live data. So you have a query that you run against static data set on historic data, and you run the same query. You don't have to change anything. You run the same query on live data. So this is obviously makes a big difference, right? Whether you can use the same query or not, or whether you have to mingle around with the semantics of the query. So with Flink's APIs for relational processing, we basically make sure that the semantics of the query are the same, regardless of whether you run it on a batch input or on a streaming input. Both APIs, as I said, are two entry points to the same library. And how does this work? So just a few words about the internals. We're using Apache Calcite, which is an optimizer framework. And it's an Apache top-level project. And it's fairly widely used in the open source space. So many projects who provide a SQL interface are based on Apache Calcite. For instance, Apache Drill uses Calcite, Apache Phoenix, also Storm uses it. So there are a lot of projects that basically use Calcite, and Calcite can basically take a lot of advantage from all these diverse use cases. Both APIs are using the same type system. They're using the same code generation. And they're also using a lot of the common things like interfaces for user-defined functions, to define connectors. We call them table sources and table sinks. So all of these are shared across the Table API and SQL. So how do these queries look like? What's exactly the difference between table API and SQL? Why do we have two APIs to do basically the same thing? So this is an example of a simple query in the table API. And as you see, this is the table API is a language integrated query, a query language, which means that you don't specify your query as a string as you would do it in SQL, but rather you have something like we call it table object, and this table object provides different methods with which you can modify the table, or you're not modifying the table, but you're creating you derive a new table from the previous table by applying relational operations on it. So in this example here, we have a so-called table environment, which basically provides the entry point for the API. We say scan clicks. Clicks is a table that we registered in the table environment. The table environment has the catalog, similar basically to a database system. So we scan the clicks table, which gives us back a table object. On this table object, we can now apply a filter operation. Here, clicks is a table which contains a little bit of clickstream data, so we can filter for URLs, which are like this certain pattern here. Then we can say a group by, and we say select and compute an aggregation. So this is a fairly simple query, and you. In this example, this is like the Scala version of the table API. There's a Scala version and a Java version. And in this example, you see that all of this is nicely embedded into the language, and all of that is also checked by the compiler. In contrast, the SQL interface looks as you would expect it. So this is plain standard ANSI SQL. So you basically write a string and then submit that. And if you want to have a standard SQL interface, then you can also use SQL. And both queries are internally translated into the same representation, into the same logical plan. And then from there on, the system does not even distinguish between table API queries or SQL queries. From there on, everything goes the same way. This is also why it's fairly simple to have both APIs. All right, as I said, table API and SQL are unified APIs for batch and streaming, so it doesn't matter whether clicks here is a file that we read from HDFS, or whether it's a database table. We have, if you have some table source which would read that from a MySQL database or whatever, any other kind of database, or whether this is a stream, a Kafka topic, or something else. So it doesn't really matter. The semantics of what the query computes will be the same in either case. So how does it work if clicks would be a table? So this is fairly simple, basically exactly as you would expect it to happen. So we have this example table here. We have 4 rows here. 2 of the users occur twice. So in this case, Mary occurs twice. Bob has 1 entry, and Liz has another one. So if we apply this group by user count URL query here, we get a count of 2 for Mary, Bob 1, and Liz 1. So, but what would happen if we now get more data into our file? Well, we would just have to run the query completely over again, right? So maybe we get our click streams in hourly batches, then we would have to run the query again. This is like how many reporting applications work these days. So you get updates in intervals, and then you have to rerun your query over and over again. Well, what would happen if this clicks table would be a stream? So there are many sources. In fact, like most of the data sources are generate the data as streams. There is usually not such a thing that gives you here. This is my 1 gigabyte of data. Please analyze it. Usually the data is generated as a stream. What we would like to have is that if this data comes in as a stream, continuously updated, then we would like to have, of course, the same results if we would that we would get when we would batch all the data in intervals and rerun the query over and over again. But how can we actually do that? Is it actually possible to query a stream just like a static table? Well, usually people start with these observations and they say, well, actually, this might be a little bit tricky. Well, because SQL was not actually designed for streams, right? All the relational algebra is based on relations which are bounded multisets, whereas streams are infinite sequences of events coming in. Traditional database has access to all the data. When you run a query, you hit the button, you say select something, you hit the button. At that point in time, all the data that will be analyzed by the query is already stored in the database. In contrast, when you run a streaming query, you usually say, here, this is my stream, and you want to process data as it arrives. So the data has not even arrived in the system. So this makes a difference because the processing system doesn't really know what will come in the future. And a traditional database query, when you send it, as I said, all the data is there. You run the query terminates at some point in time and gives you back the result, whereas in a streaming workload, you usually start the query, and then you want to have continuously, the query doesn't terminate, but instead you want that the query returns continuously the results based on the data that is streamed into the query. Well, despite all of these things, database systems are actually running SQL queries on streams for quite some time. There is this feature of materialized views. Who is aware of materialized views or what they do? So essentially, materialized views, okay, most of you know that, are basically similar to regular views, but those views are persisted in the database system, right? So instead of having a virtual view, which you can use in a query and which is then expanded into its view definition query when the query is translated, you have the actual data which is stored in the database system. Whenever you access the materialized view, you're accessing exactly the data that is already pre-computed. And what does it mean? This basically means that whenever you the base relations of the view definition are changed, you need to update also the materialized view because you always want to have the latest data in your materialized view, right? And database systems have quite sophisticated database systems have very advanced algorithms to actually keep these materialized views up to date. And what they basically do is if you think about it, they're running SQL queries on a stream of data. But the stream of data is not like the raw data. Instead, you have to think of the stream of data as a stream of modifications to the base table. So it's basically running a SQL query on a changelog stream. So you have your base relations. And whenever something changes in your base relation, you insert a new row, or you delete a row, or you modify a row, then this modification has to be carried over in the materialized view. So database systems actually do what we also want to do, right? So they're running SQL queries on streams of data, but the stream is basically all the modifications that applications or users apply to the base relations. And then the materialized view is basically continuously updated as the base relations are updated. In Flink, we modeled this, basically this concept, as something that we call dynamic table. A dynamic table is basically a table that changes over time in contrast to a static table. And whenever you run a query on a dynamic table, then the result of the query will also be a dynamic table, which will be updated as the base tables are updated. So you see that's basically exactly the same description that I gave for materialized view maintenance. It's basically the same thing. So these queries on a dynamic table don't terminate, but instead they maintain the result of the SQL query always with respect to the updates of the input table. What do we have to now to basically make this work in a streaming system? Well, we need some way to convert data streams into these dynamic tables and convert them back. So we need some way to basically say, okay, I have a data stream here, and now I want to turn this data stream into a dynamic table on which I can run a query. I get another dynamic table back of that, and this dynamic table then I want to again convert back into data stream or write it into some other kind of system. In Flink we have two mechanisms to convert a stream into a dynamic table. The first one is the so-called append mode. In this mode, we basically have a raw event stream. So we don't have like something like a changelog stream, as you would have in a database system where you say, okay, this is an insertion, this is a delete, this is a modification. But instead, we just have the raw results, and we simply and the logical model here to derive a table from the stream is by simply appending each event that comes through the stream to the table. So we have an ever-growing table, which is just grows as more data arrives. So here's a simple visualization of that. On the left-hand side, you can see like the stream with events which have a certain schema here. So of course, all the data needs to have the right format to be converted into a relational table. And this is basically then mapped one-to-one into a relational table, into a dynamic table, which grows with each event that arrives on the stream. So this is the first conversion mode. The second mode to convert a stream into a table is called absurd mode. And here we basically define, we say, okay, we have one of the attributes or one or more attributes in the stream are primary keys on the stream. And whenever we see a record coming from this stream, we insert it into the table if it's a new key, or we replace the existing value if the key is already known. So this is basically a table which updates its entries based on the row. Whenever we see something new, a new key, it's an append to the dynamic table. And whenever we have a key which is new, which we already have in the dynamic table, we replace the current value by that. So in this case, the size of the dynamic table is bound by the cardinality of the key attributes that you receive from the stream. So once we have that, we can now basically run queries on the dynamic tables. So how would that look like? So imagine we have this simple query that is basically the same as we had before in our example. So we have a simple group by query, group by count URL. We simply group by something and we count how many entries we have in the group. We have again on the left-hand side is the input table, on the right-hand side is the output table. And if we now get the first row on the left-hand side, we get a user Mary, C time is the click time here, and some URL. And now we get an entry on the right-hand side with a count of 1. So next, we get another entry. Now it's a user Bob. We get a new entry over there. We get another user for the first, another user for Mary. So we increase the count there to 2. We get a completely new user. We have another count of 1, and so on. So we basically increase the counts as more data arrives here. So in this case, we see that the rows of the result table need to be updated, right? So there is, whenever we get a new row as input, we have to update either insert or update a row in the result table. So this is fairly straightforward, but now, what is about like common streaming operations like Windows? How would that be represented? So when you talk about streaming, many people the first or one of the first things that people come into their mind is, okay, how can you do windowing? How can you compute aggregations over a stream? And this usually the answer is you have to use Windows for that. So that's also possible with the DataStream with the table API and SQL. In the table API, such a query would look like that. So we have again the scan operator to retrieve the table from the registered clicks table, which could again be backed by a stream. In this case, it's backed by a stream. Then we specify a window here. We say tumble over 1 hour on click time. Click time is the time attribute of our table, and we assign an alias to this. So we call this window, it's called W. Then we say group by. We group on the window and an additional attribute. And finally, we again, as in the queries before, we do a select on the groups, and we say select user, which is one of the grouping attributes. We say w_end, which gives us the end timestamp of the window in this case, and we say URL count, which is again the number of attributes in the window for the user at that point in time. In SQL, this looks fairly similar. So we're using here these functions, these group window functions. They're called tumble and tumble end. These are part of Apache Calcite. So Calcite implemented or provided these methods, and all other streaming systems that will implement stream SQL based on Apache Calcite will likely use these functions as well. So they're not exactly yeah. So in this case, you basically see we say group by tumble, click time interval 1 hour. Again, the tumble, the window clause is going into the group by clause here, and in the select clause again we have something which fetches the end timestamp of the window. So how would then such a query be executed in Flink? So again, we have the input data on the left-hand side. The query is in the middle. It's exactly the same as before, and the result is on the output and on the right-hand side. So we get a couple of rows as input, and all these rows are now have timestamps between 12 o'clock and 13 o'clock, and these will then be grouped together into two result rows. One for the first user, which is Mary here, with a count of 3, and Bob will have a count of 1. And you see that the end timestamp there is 13 o'clock, which is like the end timestamp of the window. So the window goes from 12 to 13. This is the end timestamp of the window. And now, as more data arrives, we append more rows to the output table. So in this in the window which from 13 to 14 o'clock, we have 1 row for Bob and 2 for Liz. So we get a count of 1 and 2, and so on. And in this way, we can the system computes a window over the streaming table, which is appended. So the table on the left-hand side is always appended. You always get more data, right? And the observation here is in contrast to the previous example where we had to update rows. In this case, rows are simply appended to the result table. So, and why is it that we can actually append these rows now? So what's the big difference, like semantically, from between the first query and the second one? Both are like grouping queries which do simple account aggregation. Well, the difference here is that this ctime attribute is an event time attribute. If you used the DataStream API before, you're aware of the concept of probably aware of the concept of event time and event time timestamps. So in this case, this ctime attribute, which is used in the tumble clause here, is such an event time attribute, which means it is guarded by watermarks. So this attribute is almost monotonically increasing, might be a little bit out of order, but the watermarks basically fix these out of orderness and give at certain point in times give the system a way to determine the current time, and to infer that no records with a lower time will be observed. And this, by using these watermarks, the system can infer, okay, now I've seen all data that I need to see in order to perform the computation. I can do the computation and emit the result, and I don't have to emit an update afterwards. So internally, these event time attributes are represented as special types, but user-facing, they are handled as just usual timestamps. So there's not so much to worry about. The difference when using these attributes is actually that the system can translate the query into certain into more specialized execution plans, because they know a little bit more about these timestamp attributes than they would know about like common or regular timestamp attributes, which could have any value at any point in time. Okay, so now we covered like the two interesting cases of how we can query these dynamic tables and get a new dynamic table from such a query. Now we want to convert a dynamic table back into a data stream. How can we do that? As we've seen in the first query, a query might result in a dynamic table which has to update its rows, right? So it has to somehow indicate to the downstream system that a previous value has become invalid, and there is no new value. If you think of the first aggregation query, whenever we saw a new record for some user, we had to increase the count for this one, right? So these updates somehow need to be encoded in the downstream system. And in Flink, these conversions are basically done with two kinds of modes, and these modes are somewhat inspired by how database systems use logs in order to restore or replay or failure recovery in database systems. So there are two modes to do that. Usually one of them is called redo logs, which basically store the new records in order to be able to redo changes in case they got lost. And the other one is called undo mode, which means that the database system remembers the old values of the rows in order to be able to undo changes in case a transaction has to be rolled back in case of a failure. And these modes are like the inspiration for the modes that we implemented in Apache Flink. So the first mode is called redo undo log, because the stream basically exposes both the old record and the new record. So whenever we do an update, of a row, whenever we first send a retraction value, which basically means please remove this value, and then we send a new record which says here this is the new value. In this case, we have our first query here as an example, and we have this input table, and we see that when we get the first row in here, which is for the user Mary, we see that we insert Mary with a count of 1 in the result table. Then we get a new row, which is Bob. We again say plus, here is for insert. We insert another record with Bob 1. And when we get the third record, which is again for Mary, we see here this basically triggers the emission of 2 rows to the output stream. The first record will be minus Mary 1, which basically says, please remove this. This is no longer valid. And then we say here, please insert this record. For Mary, we now have a count of 2, and so on. So whenever we have to update an existing record, we send out a retraction value, which removes a row, and then an insertion. So this might seem a bit inefficient, because for one input row, we emit two rows to do an update. And that's why we also support this redo mode, in which we basically just send out one value. But this one new record to the output stream. But this mode has a special requirement. This mode basically requires that the downstream system needs to be able to access data or update data based on a key. So in this case, we know based on the query that we have a unique key on the dynamic table, which is the output here, and the unique key will be the grouping attribute here. So there will always be a single entry for each user. So, and based on that, we can then simply send out records and say, please upsert the row for this key. So we basically just replace the old value with a new value, but the downstream system needs to be able to access its data by key, and also needs to know about the key. So can we run any query on a dynamic table? Well, usually not. So there are some space and computation constraints. So one thing is that in order to run these queries, depending on the velocity of the stream or the data volume of the stream, that the state size that the query needs to maintain in order to answer the query or compute all results usually might grow infinitely, and depending on the data volume of the stream, might grow very, very large. So if you look at this query, for instance, if we would imagine that our clicks table would in addition also have something like a session ID attribute, which is automatically generated for each session, then this would usually be an attribute that has a very, very high cardinality. So we would basically, and would not reoccur so frequently. So in this case, the query engine or Flink would need to forever keep the count for each session ID and could never remove it, because it always would have to expect there will be a new record for this session ID. Another example for a query that is very hard to, or cannot be implemented in a streaming fashion is, for instance, a query where one update in the input table might trigger many computations or many updates on the output, right? So when you have a single record being inserted in your input table, and then you have to basically recompute the whole table, this simply doesn't scale. And one example here is such a simple rank query, where you order your result table by a certain attribute, and then you want to have a rank assigned to this. Imagine you get a new row right at the top, then you have to adapt all the ranks of all the following records. So this is a query that cannot be computed or answered in a streaming fashion. So while the first thing can be, or the first issue can be somewhat addressed, the second one is really hard to address, because it basically it's in the semantics of the query that you have to do exactly these changes. So what can you do to bound the size of a query? So one of the things is what you can do is, for instance, you can try to adapt the semantics of the query a bit, depending on your use case. That's possible. Sometimes it's not. For instance, by bounding the relevant data of the stream. So for instance, you could say, okay, I'm only not interested in the complete history of the stream, but I'm always interested in the last 24 hours of the stream. So I could basically say, as the stream moves, I always keep the data that my query computes on the last 24 hours. So that would be one way to basically bound the amount of state that you need for your query. And the other one is to basically trade accuracy of the result for the state of the size. So you could, for instance, if you go back, if you look at this example here for the session ID, if you know that a session will be over or terminated anyway after like 24 hours, you can automatically remove sessions that have been invalid for 24 hours, remove the state for them, and just go on, because you know there will never be an update for this row again. This is something that the query engine by itself does not know, but you as a user know the semantics of this stream and can then basically give a hint to the system to be able to execute this query more efficiently. So what's the current state of Flink SQL support and table API? So all of this is rapidly evolving. So there is lots of interest in the community. We have many contributors from, as you've heard in the keynote, from Alibaba, Huawei is contributing, Uber is contributing. So there are many users interested in these APIs and providing contributions, new operators, bug fixes, feature requests. So there's tremendous activity in this component of the Apache Flink project. In Apache Flink, we released many operations which are centered around aggregations. So we released group and over window aggregation. So the over aggregations, as you know them from window aggregations, as you know them from SQL. We released these non-windowed aggregations, which was the first example where you don't specify a window, which result in updates of changes. User-defined aggregations were a major contribution as well. In the next version of Flink, Flink 1.4, will add window joins, so you can do joins between streams in a streaming fashion, and we'll also rework the connectors APIs, the table API, table source and table sync interfaces. All right, so what can you actually build with all of this? So one thing is, for instance, a continuous ETL pipelines. So you can continuously ingest data, apply transformations, window aggregations, with the next release also joining streams together, and write these files, write the data to files, to Kafka, to Postgres. This basically means that you want to have append-only results, which means you kind of like rely on the watermark features, which give the system a way to know when a certain computation is complete. So this is for these kinds of use cases, the watermarks are very important. Another kind of use cases is to build dashboards, reporting, or event-driven architectures and applications with this, where you're likely to rather use the feature that Flink is able to maintain basically a materialized view based on a stream. So you get the stream into your query, and the query then maintains the materialized view and emits the data to a key value store, to a database, or a compacted Kafka topic, or even keep it in Flink's queryable state inside of your application, and then you can query the result table with point queries from your application outside. All right, to wrap up, both APIs, Table API and SQL, support many of the streaming use cases. So a lot of the common things that people would like to do to perform streaming, or to do streaming applications can already be solved with the Table API. The Table API has support for Scala UDFs, Table A UDFs, and user-defined aggregation functions. So there's also ways to plug in custom code into these APIs. All the operators are code-generated. It's efficiently executed, and yeah, as I said, so you can actually solve quite a few challenging applications with these APIs. Yeah, and I'll encourage you all to have a look at the APIs. Give us your feedback if you find something that is missing or something that is unfortunately not working. We really appreciate it. Okay, thanks.
Thank you. Do you have any questions? Yep.
Hi, that was a great talk, thanks. You showed that on Flink 1.4 there will be support for window joins.
Yes.
Are there any plans for non-window joins?
Yeah, so there is already a community discussion about that. I'm not sure if we'll make it for 1.4, so that's why I didn't include it here. But there's already a pull request open. There needs a little bit more discussion, but this will definitely be added. Not sure if we'll make it for 1.4, but it will be there definitely. Yeah.
Okay, cool, thanks.
Hi, can you deal with event arriving not in the right order?
Yeah, so actually this is basically based on the, this is what the watermarks are about. So if you have defined your timestamp attribute to be like such an event time attribute, then you can certainly deal with that, yes. So if it's within the bounds of the watermarks out of order, of course, and there will also be appropriate configuration parameters to widen the tolerance gap, so to say. This comes at cost of latency, of course, because you have to wait a little bit longer until you're sure that you've seen all data. But that's the usual trade-off that you have with watermarks. But yeah, of course, out of order events can be processed.
Yeah. You said that when you are using a window function, then the result is only, or result table is only appended. Does this effectively mean that if you have a window for 1 hour, only every hour this result table is updated?
Yeah, you can do it like that. So right now this is how it works. We'll also add configuration parameters to allow the emission of early results. So, but then again, you will have to deal with the updates. So there will be ways to say, okay, I want to have my first result 30 minutes after I started the computation. Then you might get the first approximation after 30 minutes, and then you get your results, let's say, every 5 minutes until you're confident that you have the right results. So there will be the same mechanisms that you also have in the DataStream API for early emission and also late data handling. If you want to have a result and then later you get a late value that you then have to update. But then again, you have to this will be again implemented as retraction values. So whatever is your sink has to be able to deal with these retractions. So the queries are basically, all of this is translated into DataStream programs. So it's the same, basically, yeah, it's hard to tell. So you basically, internally, the queries are translated into DataStream programs. We haven't run like a comprehensive benchmark on these. So.
Great. Any more questions? Thank you.